Hello everyone, welcome to Module 3 of the GPU Teaching Kit. We're going to introduce CUDA parallelism model in this module, and we're going to start with lecture 3.1 on kernel-based single program multiple data programming in CUDA. The objective of this lecture is for students to learn the basic concepts in a simple CUDA kernel function. In particular, we're going to introduce the declarations that they will be making in the function, and we're going to introduce more about the concepts of built-in variables in CUDA, and then we're going to have a more concrete description of the thread index to data index mapping in a one-dimensional kernel structure. Here we show a complete simple CUDA kernel which does vector addition. And we have already introduced the vector addition computation in Module 2. Here we just show that how we can write a parallel kernel in CUDA to perform vector addition in massive parallelism with massive number of threads. Here we see that the function is declared with a keyword underscore underscore global underscore underscore. There are two underscores on each side. We're going to declare the kernel function as a void function. In CUDA, the kernel functions cannot return any value. And just like any other C functions, this function is going to take input parameters A and B. So these are pointers to array A, vector A, and vector B. And it also takes another pointer, which is the output vector C. And it also takes an integer value n, which gives the number of vector elements that need to be added together. Remember that we already talked about memory allocation and memory copying. So by the time we invoke this kernel function, we assume that the input vectors A and B have been allocated and transferred into the GPU memory. So these pointers are pointers into the GPU global memory. Similarly, we also assume that the memory allocation has been done for the C output vector, and so this is a pointer to the global memory where the kernel function can write the output elements. Now we see there is a very familiar index calculation expression that we have already introduced in Module 2. Recall that this index evaluation allows all the threads to form a uniform coverage of the integer values from 0 to the maximal value that we want in that we can compose out of the block index and the thread index. So we see that we have a familiar expression blockdim.x times blockidx.x. And then that's essentially equivalent to the area code of the cell phones. And then we have the thread index, which is the local number. And these two together give us the globally unique uniform coverage of a whole range of integers. Then the next statement tests whether the index form is less than the number of elements. So essentially, we may have more threads than the number n. So only those threads with indices that are within the actual range of valid elements in A, B, and C should participate in the generation of the output C element. So that's why we had that condition test. This slide shows the vector addition kernel launch in the host code. And remember that we had a traditional C version of the vector addition where there was a sequential loop that goes through each pair of A and B elements and produce a C element in each iteration. Now, once we have the GPU kernel, we no longer have that sequential loop in the vector addition function. Instead, the vector addition function becomes a outsourcing agent. We assume that we have already performed allocation for A, B, and C in the GPU global memory, and we also perform data copying from close to GPU global memory for the input vectors A and B. So we omitted those statements that we have already shown in Module 2 for clarity here. Now we can focus on the kernel launch. The kernel launch is very similar to a C statement, except that there is a configuration parameter setting in between the name of the function and the actual C parameters. So these are what we call the configuration parameters. And you see them in between 3 less signs and 3 greater signs in the kernel launch statement. So the first configuration parameter sets the number of thread blocks in the grid, and the second configuration parameter sets the number of threads in each thread block. So the total number of threads that we have that we launch will be the product of the first parameter and the second parameter. We see that we use a ceiling function of n over 256.0, and this means that we want to make sure that we launch enough number of thread blocks so that we have enough threads to cover all the vector elements. We assume that the program developer, has set the thread block size to be 256. So that's the second parameter. That means that every thread block has 256 threads. So let's say if we want to have 1,000 elements processed, and every thread is going to be processing one element according to the previous slide, then we need to make sure that we have at least 1,000 threads to process these elements. So the thread blocks each will come with 256. So in order to cover 1,000, we need to have 4 of those thread blocks, which give us 1,024. So by using the ceiling function, when we divide m by 256.0, remember this needs to be a floating point number. If you use an integer number here, it will actually do a truncation, and then it will not give you the additional thread block that you need in order to cover the last section of the vector. So here, by using the ceiling function, we will generate 4 thread blocks, and each thread block will have 256. Therefore, we have 1,024 threads covering 1,000 elements. We will have 24 threads that will be extra, and then they should not participate in the computation, as we will see, as we already mentioned in the previous slide, where there is a check for each thread to check its index and see if that index is within the valid range specified by n. The developer may actually choose to initialize the number of thread blocks and the number of threads in a block in a separate statement. In fact, what we had in the previous slide is a one-dimensional case. So by providing one value in each of the parameter position, we assume that that value is going to be used for the x dimension of the three-dimensional variable. But in general, we may be launching 2-dimension or 3-dimension thread blocks. So in those cases, it is better to initialize all the dimensions in separate statements and then use the resulting struct variable in the dimensional parameters, configuration parameters. So here we show an equivalent way to express the ceiling function, which is you can take an integer n and subtract that value by 1 and divide by the 256 in this case, or whatever number of threads you would like to have in a thread block. And then you take the quotient and then you plus 1. And this will give you the equivalent of that ceiling function without using a floating point calculation. But this is more verbose, and so you may not be also as clear as the intention that we expressed in the previous slide. And obviously, this is still a one-dimensional computation, so we're going to have 1 and 1 in the y and z dimension for dim grid. And for dim block, this is the struct variable to specify the number of threads in a thread block in each dimension. So again, we only have one dimension and we want 256 threads in a thread block, so we're going to just have 256 and 1 and 1. Now we can use these two variables in the as the configuration parameter, and that will achieve our goals. Keep in mind that these variables names are arbitrary, so we just happen to pick dim grid and dim block for clarity, but we can call them dog and cat as long as the dog is used in the first configuration parameter and the cat is used in the second configuration parameter, as long as we're consistent in the definition and use of these configuration parameter variables. You can give them any name you like. However, we will have a similar set of variables in the kernel that are actually predefined, and so we will not have flexibility in when we get to the kernel functions. So now we are ready to summarize the execution model behind the CUDA kernel launch and kernel execution. So we see that on the left-hand side, we have a host code of vector addition that will be launching kernel. And you have already seen the setting of the configuration parameters and the kernel launch statement. So when we execute the kernel launch statement, the GPU hardware creates a grid of threads, and we're showing in the center bottom. And then these grids of threads will each execute, every one of these threads will be executing the kernel function on the right-hand side. But every thread block will have a combination of block IDX and the thread IDX, so that all the threads in the grid will be able to form a unique index value I, and so that they will access a different pair of A and B elements and produce an output C element. As we mentioned before, all of them will also be using I in the decision about whether they will be participating in the addition. So in our example, if we have 1,000 elements in A, B, and C, so the first 1,000 threads, 256 in block 0, 256 in block 1, 256 in block 2, and then finally, 256 minus 24 of them in block 3 will participate, and 24 of the remaining threads in block 3 will not participate. And this is what I referred to in the in module 2, that this I index will be used by each thread to make their individual access into the data structure, as well as making their individual decision whether they will participate or not participate in some of the computation. Now we're ready to close on the CUDA function declarations. Now we have seen there are functions that are host functions, such as the vector add function that performs the outsourcing, and we have a global function that is a kernel function. So in fact, there are three types of functions in CUDA, and we have only seen the host function and the kernel function so far. So just to reiterate, the second row shows a declaration of a kernel function. As we have seen, these kernel functions are preceded with underscore, underscore, global, underscore, underscore. And these functions will be executed on the device. These are the parallel functions that the kernel can, the host function can call. So they can only be called from the host, as we show in the third column of the table. And the bottom one shows the host function. And these are the traditional C functions. And they're preceded by underscore, underscore, host, underscore, underscore. And these host functions are executed on the host and only called from the host. The top row shows an additional type of function in CUDA that we have not described, which is underscore, underscore, device, underscore, underscore. And these functions are functions that can be called by the kernel function in order to perform some some sub-computation for the global for the kernel function. This allows us to use the more better engineering practices and abstractions and so on when we compose a GPU kernel function, in the for more complex kernel functions. So these device functions are executed on the device and can only be called from the device by a kernel function or by other device functions. So a couple things that we also should note. Device and host can be used together. That is, we can actually mark a function as both device and host function. In that case, there will be two versions of executable forms of this function. These functions generated by the compiler. One will be used on the host, and one version will be used on the device. And the second one is the host designation underscore underscore host underscore underscore is optional. And so if we don't use that keyword in front of any function, if the function is not preceded by any of the three keywords, then the host function, that function is treated as host function. And this is because we expect that many C programs are existing C programs, and we would augment these C programs to use CUDA kernels. So many C programs will have their functions originally defined without any keyword. So those functions should default into host function. Whereas if we intend to have some of the functions generated into device functions, we should just add the keyword underscore underscore device underscore underscore in front of the function. But if we added the device designating keyword, then we still want to have a host version, then we also need to add the underscore underscore host underscore underscore. We need to have both in front of it if we truly want to still have a host version of the executable form for that function. Now that we know how to declare functions and host functions, kernels, and device functions, we are ready to look at how we can compile a CUDA program for execution. So on top of the figure, we see that the CUDA code is an integrated C program with CUDA extensions. Some of these functions and so on will be kernel and device functions. So we send the entire program through the NVCC NVIDIA C compiler, and then the NVCC compiler will separate out the host functions and device functions and kernel functions. So the host code will go through a host C compiler of your choice with the linker, and this will be typically GCC or Intel ICC or some vendor functions that there may be some other C compilers that you prefer to use from other vendors. On the other hand, such as Microsoft C. So then the device code will be in the form of PDX, and then you will eventually go through a device just-in-time compiler at runtime to produce the actual instruction set architecture code for the particular version of the GPU. So in the end, these two parts will be linked together and executed on a heterogeneous computing platform with CPUs and GPUs and so on. This concludes lecture 3.1. Thank you.